All right. So before we get into the full-blown ice table calculations, there's one more definition that I want to share with you. And this is percent ionization. Your book sometimes calls it percent deprotonation. Um, I'd say that is a less common term. But the idea behind it is we compare the amount of hydronium generated by the um, reaction with the acid into the water. And we compare that by looking at, well, okay, what was the concentration of hydronium at equilibrium compared to the initial concentration of the acid? And what we'll see is that for a lot of these weak acids, this percent ionization is going to be in the 5 to 10% kind of range. Now, part of that is concentration based. So some when we get to lower concentrations, generally we see higher percents of ionization just because, well, the numbers are smaller. Um, but generally speaking, for weak acids here, we're going to see things generally less than 10% for their percent ionization, generally speaking. And comparing that to strong acids, where strong acids we have over 99% ionization taking place because, again, the equilibrium is so far shifted to the product. So we want to bring this up primarily because this is one of those calculations that you can see, and the calculation for it isn't terribly difficult, but it's just something that you want to be aware of. So, with that in mind, let's take a look at some practice problems that we things that we could be asked to do involving acid or base equilibria and kind of the directions that we can go. So, this is a very common question. What is the pH or what is the expected pH of a particular solution of a weak acid where we've got this Ka value coming out here? Now, if this were a strong acid, all that we would do is take that concentration, say, okay, 1.2 molar acetic acid. Well, it's a strong acid, so that would mean 1.2 molar hydronium, and I would just calculate the pH directly off of that. But since it's a weak acid, we're going to have to go into ice tables to figure out how much hydronium is present at equilibrium so that we can calculate the pH that way. So we need to set up our equilibrium first. Acetic acid, which we're just going to abbreviate HOAC, reacts with water to make hydronium and the acetate ion. So setting up our ice table, our initial concentration of acetic acid is 1.2 molar. We don't care at all about the water because it's not a reaction participant. Our initial concentration of hydronium is 0. Our initial concentration of acetate is also 0. So, pretty obvious which direction this is going to go. We're going to add products. So we're going to add some measure of hydronium, some measure of acetate, and we're going to lose some amount of acetic acid. So at equilibrium, our concentrations are going to be 1.2 minus X for acetic acid, X for hydronium, and X for acetate. Now, one of the things that we can do that help us along with these kinds of calculations is a lot of these weak acid, weak base equilibria are susceptible to the 5% rule. So if you remember from the end of last chapter, the 5% rule tells us that we can ignore the negative x term here if we can prove that it's going to be negligible. So 1.8 times 10 to the negative fifth is our value of k. Divide that by 1.2 multiplied by 100. And we're going to get a pretty small number here. 0.0015%. That's far less than our 5% threshold, so we can safely ignore the minus x. And so setting up our equilibrium expression now, 1.8 times 10 to the negative fifth is equal to x times x over 1.2. Multiplying each side by 1.2. 1.2 times 1.8 times 10 to the negative fifth gives us 2.16 times 10 to the negative fifth. X times x is x squared. Take the square root of both sides. We get x is equal to two significant figures, 4.6 times 10 to the negative third molar. Question asks us to calculate the pH of this solution. So pH would be equal to the opposite of the log of the hydronium concentration, so 4.6 times 10 to the negative third. Two sig figs in my concentration means 2 decimal places in my pH. So the pH of this solution is expected to be 2.34. Now this is the way that we would solve the ice table and answer this question specifically. Understand, we can answer all of the other kinds of questions that we would have been asked about ice tables previously. So for example, if I wanted to know the equilibrium concentrations of each of these things, knowing X, I could now say that 4.6 times 10 to the negative third molar is the concentration of hydronium. 4.6 times 10 to the negative third molar is the concentration of acetate. And if I take this off of 1.2, I'm still going to get 1.2 molar as the concentration of acetic acid. So I could do all of those calculations just like we did last chapter. If I wanted to calculate percent ionization, like what was on the previous slide, again, it's not asked for here, but percent ionization is a relatively easy calculation. We would take the concentration of the hydronium divided by the concentration of the initial concentration of acetic acid and multiply it by 100. So 4.6 times 10 to the negative third, divide by 1.2 molar times 100. We would get 0.38% ionization there. So just because we've changed the framework of the equilibrium, focusing on acids and base acids in this case instead of a gas phase reaction or a different kind of chemical reaction in solution, doesn't mean that any of those underlying principles go away. They're all still there. But now we have some different ways of expressing those kinds of ideas, like pH, like percent ionization. So we're taking what we already know, and now we're just adding a couple of things to it and finding some ways to be more specific about the equilibrium's position and the expression itself. All right, let's take a look at another example problem. Here we have the Ka for 0.085 molar phenylacetic acid if the pH is 2.68. We're also asked to determine the percent ionization. So this is along the same kind of lines as some of the problems that we saw last chapter where we had to solve for K. Easiest way to set it up is to start with our equilibrium expression. Now, if you find yourself in this situation where you don't know what the chemical formula for phenylacetic acid is, you can do what we did in the previous problem. In the previous problem, we used an abbreviation. We can use abbreviations here as well. So it doesn't matter that we don't know what the phenylacetic acid is in terms of its formula. We can write an expression that follows the general principle of what an acid would look like. So phenylacetic acid, let's just abbreviate it, HPhen. The H is going to react with the water to make hydronium. And the resulting phenylacetate ion, we'll just call it Phen minus. It's the molecule minus the hydrogen ion. Now we're going to set up our ice chart in the exact same manner that we did before. 0.085 molar for the phenylacetic acid. Don't care about the water. Initial concentrations of the two products are 0. We know that we're going to lose some amount of phenylacetic acid, gain some amount of each of the products. And so at equilibrium, we're 0.085 minus X, X, and X. But here's the kicker. We know something already about the position of the equilibrium because we've been told what the pH is. And if you recall, pH being the opposite log of hydronium, the only way that we can know the pH is if we know the hydronium concentration. We just got to figure out the way to extract it. And this is where our calculations on Friday come in. Hydronium ion concentration is equal to 10 to the negative pH. So 10 to the negative 2.68. We get a hydronium concentration to two significant figures of 2.1 times 10 to the negative third molar. With that in place, we can go back and solve the rest of the ice table. So since we know this value of x, we know that it's going to be equal to this x and this x. And if we substitute it in for this x, 0.085 minus 2.1 times 10 to the negative third, keeping our sig figs intact, it's now 0.083 molar. We now know all of the equilibrium concentrations, so we can figure out the value of the equilibrium constant. K is equal to 2.1 times 10 to the negative third for the hydronium, 2.1 times 10 to the negative third for the phenylacetate, 0.083 for the phenylacetic acid. So putting those together, divide by 0.083, the two significant figures again, we get 5.3 times 10 to the negative fifth. So that's our value of K. Now we need to do the percent ionization calculation. 2.1 times 10 to the negative third for the concentration of the hydronium, 0.085 as the initial concentration of the acid. Square those up together, so 2.1 divide 10 to the negative third divided by 0.085, multiply by 100%. The two significant figures, 2.5% ionized. So if we compare percent ionizations, the first example was 0.38%. This one's 2.5%. Why the difference? Well, we can see that the Ka values are not that different from each other. This one does have a slightly more acidic Ka, 5.3 times 10 to the negative fifth compared to 1.8 times 10 to the negative fifth. But the bigger difference here is the concentration. Concentration of 1.2 molar compared to the concentration of 0.085. Generally speaking, as our concentration comes down, our percent ionization usually does go up. Especially if we're comparing K values that are really similar to each other. Now, if we've got K with a 10 to the negative second versus K with a 10 to the negative 12th, we're going to see higher ionization with the stronger acid. But if I'm comparing similar things, concentration makes a big difference. All right, any questions with these first two examples? All right, then let me spin it around on you here. Calculate the pH of a 0.02 molar benzoic acid solution. The Ka for benzoic acid is 6.3 times 10 to the negative fifth. All right. So setup for this is pretty similar. We got benzoic acid reacting with water to make hydronium. And the benzoate ion. So initial concentration would be 0.02 for the benzoic acid and nothing for anything else. We're going to lose some benzoate, gain some of the rest. So 0.02 minus X for the benzoic acid, X for the two products. Question is, can we ignore that minus X term? And so if you did the calculation, 6.3 times 10 to the negative fifth, divided by 0.02 times 100%, you get 0.3%, certainly less than 5. So we can ignore that term. So 6.3 times 10 to the negative fifth is equal to X times X over 0.02. Multiplying both sides by 0.02. We get 1.26 times 10 to the negative sixth is equal to X squared. Square root both sides. X is equal to two significant figures, 1.1 times 10 to the negative third molar. So concentration of hydronium is that. So pH is equal to the opposite of the log of 1.1 times 10 to the negative third. And so you should get somewhere in the neighborhood of 2.95 for that pH. We're not asked to do all the other stuff, so we'll just ignore it here. You'll certainly get enough practice for it later. Any questions with this one? All right, just as a reminder, we can do the same kinds of calculations with the base and base ionization. Just remember that the product of this is hydroxide, not hydrogen. So let's do one practice problem with this, with bases, and then if we need to, we can do, I have a couple of others built in here as well. So here we have ammonia. Reacts with water, and it's a base, so it's going to make NH4 plus and hydroxide ion. Setting up our ice table, we have a 1.2 molar solution of ammonia and zeros for everything else. And so this is going to set up and look very, very similar to what we did with the acids. Here's the big difference between them, though. The big difference between is the fact that, okay, if we do the 5% rule, we're going to find that we can ignore this minus X term. So Let's go ahead with that. 1.8 times 10 to the negative fifth is equal to x times x divided by 1.2. So everything's looking very, very similar to that first example problem that we did with the acetic acid. 1.8 times 10 to the negative fifth multiplied by 1.2 is 2.16 times 10 to the negative fifth for x squared, square root of both sides. X is equal to 4.6 times 10 to the negative third molar. Here's where we have to remind ourselves, because it gets funky here. 4.6 times 10 to the negative third molar for ammonium, 4.6 times 10 to the negative third molar for hydroxide. Here's the thing. This is the hydroxide concentration, not the hydronium concentration. So I can't calculate pH off of this directly. I can calculate pOH. That's the opposite log of 4.6 times 10 to the negative third. And if I do that, I get 2.34 for the pOH. This is probably the most common mistake that students make with base equilibria is they assume that this is where we're done. And if you scroll back to however many examples ago, that's exactly the answer we got for the pH of the 1.2 molar acetic acid. Now, it's a weird coincidence that acetic acid and ammonia have the same K values. And that's why we get the same values for their respective functions. But what we have to remind ourselves is that this is pOH, not pH. To turn it into pH, we got to subtract it from 14. So the pH of this solution is actually expected to be 11.66, not 2.34. And the thing that you have to remind yourself of is that if I'm dealing with a base, pH ought to be greater than 7. And so if you stop at pH 2.34, immediately something should be kind of clicking in your head going, wait a second, that's not right. 2.34, that's an acidic pH. I've got a base. That doesn't make sense. Where did I make my mistake? Usually the answer is you forgot to turn pOH into pH. But aside from this little wrinkle, Ka and Kb calculations we handle in very much the same kind of way. The equilibria for them are almost identical. It's just what goes into the equilibrium that makes the difference. Questions here? All right. Let's go ahead and do this one last practice problem here just to kind of reinforce it, and then we'll call it a day. So here I have aniline, C6H5NH2, and we want to know what is the pH and the concentration of hydroxide for this 0.15 molar solution of aniline with a Kb of 4 times 10 to the negative 10th. So once again, I'll tell you this. Just because we have the chemical formula does not necessarily mean that we have to use it. Now we could write this out and get the formula and whatnot. Um, in the grand scheme, though, it does not make a difference. We know that aniline is going to act as a base, which means it's going to absorb a hydrogen ion, and the hydroxide ion is going to be left behind. We can set up our ice table. We've got a 0.15 molar solution of aniline. We know it's going to lose some amount and that the products are going to gain some amount. Since our value here is 10 to the negative 10th and our concentration is relatively high, we don't need to do the 5% calculation here. We can generally assume. If you remember when we brought in the 5% approximation on last week, Thursday, we talked about the idea that if it was at negative fifth or greater, that we can generally assume 5% rule to be true, especially if the concentration is of a reasonable quantity. This is 5 orders of magnitude less than that. So we're on very solid footing here to ignore this negative x term. So 4.0 times 10 to the negative 10th is equal to x times x over 0.15. Four times 10 to the negative 10th times 0.15 gives us 6.0 times 10 to the negative 11th is equal to x squared. Take the square root of each side to two significant figures. X is equal to 7.7 times 10 to the negative 6th molar. And so to answer the second question here, what is the concentration of hydroxide? We know the concentration of hydroxide was X, which would be 7.7 times 10 to the negative 6th molar. To answer the first question about pH, we know that the pOH is equal to the negative log of 7.7 times 10 to the negative 6th. Which to two significant figures is 5.11. So the pH would be equal to 14 minus 5.11, which would be 8.89. So one thing that we can see out of this kind of work, if our KB starts getting small enough, we will start to see that pH is going to drift toward neutrality relatively quickly. Even at relatively moderate concentrations like 0.15 mole. All right, so let's leave it at that for today. So go ahead and get your last participation point out of Top Hat. And then where we're going to go tomorrow. Tomorrow is going to be kind of similar to today. We're going to talk about a general concept. That concept is, well, what happens if I have conjugate acids and bases of these weak acids and bases in water? So we're going to talk about the relationship of conjugates, and we're going to talk about how that relationship impacts the acidity or basicity of salt solutions. Because just because it's a salt solution does not mean that it is a neutral solution. And we're going to start to get into how we can predict acidity or basicity, and actually how we can calculate that acidity and basicity. And that will round out chapter 14 for us tomorrow.